Assalamualaikum and hi everyone. Alright, so today we are going to discuss on our last subtopic for this semester, that is 7.3 Solubility Equilibria. Alright, so here is the learning outcome that you should know. So first you have to define solubility, molar solubility and solubility product, KSP. Okay, then calculate KSP for concentrations of ions and vice versa. Okay, and then predict the possibility of precipitation of slightly soluble ionic compounds by comparing the values of ionic product Q to KSP. Define and explain the common ion effect. Perform calculation related to common ion effect. What is solubility equilibrium? So it can be defined that equilibrium exists between solid solute and aqueous ion. Okay, for example, so we have lead to chloride. This is exists in solid. Okay, so it's in equilibrium with its aqueous ion, that is lead to ion and chloride ion. Okay, second example is solid silver sulfide is in equilibrium with its aqueous ion, that is silver ion and sulfur ion. Okay, so here is solubility rules for common ion compound. Okay, compounds that contain alkaline metal ions and ammonium ion are all soluble compounds. Okay, and then we have nitrate ion, hydrogen carbonate and chlorate ion also soluble. Okay, for chloride, bromide and iodide are also soluble except halide of silver ion, mercury ion and lead to ion. Okay, as for the sulfate ion are all soluble except sulfate that contain silver ion, calcium ion, Sr2 plus ion, barium ion, mercury ion and also lead to ion. Okay, so here is insoluble compound, carbonate, phosphate, chromate and sulfide are all insoluble compound except compound containing alkaline metal ion and ammonium that are soluble. Okay, all hydroxide ions insoluble except compound containing alkaline metal ion and barium 2 plus ion which are soluble. Alright, so here is the example as compound that soluble in water and compound that insoluble in water. Lithium chloride is soluble in water, whereas for lead to chloride is insoluble in water. Potassium hydroxide soluble in water, whereas for the copper 2 hydroxide is insoluble. Okay, next sodium carbonate soluble in water, however calcium carbonate insoluble in water. And then sodium nitrate soluble in water, whereas for lead to nitrate is insoluble in water. Okay, here is the appearance of several precipitates. Have different colors of the precipitate. So because of the metal that is bonded to the sulfur ion. Okay, for example, cadmium sulfide, the color of the precipitate is yellow, whereas for lead to sulfide is black precipitate. Nickel hydroxide will form green precipitate, whereas for the aluminium hydroxide it will form white precipitate. So even though it has the same anion, however the cation is different and that's why there is a difference in the color of the precipitate form. Okay, solubility or solute. So we have two types of solubility and it has different units. So first is molar solubility. The unit here is mole per liter. So it can be defined as mole of solute dissolved in 1 liter of saturated solution. Whereas for the solubility, the unit is gram per liter. Can be defined as the mass of solute that dissolve in given quantity of solvent to form a saturated solution. Alright, so how to convert from molar solubility to solubility, which means from mole per liter convert to gram per liter. So very simple, molar mass times concentration or molarity. Then we'll get gram per liter. It's the unit of the solubility. As for the conversion from solubility to molar solubility, which means we want to convert from gram per liter, convert into mole per liter. So we have density divided by molar mass. So we'll get gram per liter. Alright, so next, what is solubility product constant? Okay, the symbol here is Ksp. So it's the product of the molar concentration of the ions involved in the equilibrium, each raised to the power of its stoichiometric coefficient in the equilibrium equation. So it provides a quantitative measure of the solubility of a slightly soluble salt. Okay, for example, in a saturated solution of calcium phosphate, an equilibrium exists between the solid calcium phosphate and its dissolved ions. So dissolved ion is referred to the calcium ion and phosphate ion. From here, we can write the Ksp expression. So remember, it should be concentration of the product divided by concentration of the reactant. Since the reactant here is in solid, so it is not included in the Ksp expression. And the coefficient here would become the power of. Okay. For example, like here, calcium ion. So meaning that Ksp is equals to concentration of calcium 2 plus power of 3 because it has coefficient 3. And then times concentration of phosphate ion power of 2 because have coefficient of 2. And for this one is not included because the phase here is in solid. Alright, so next, this is referred to the example of solubility product constant Ksp of selected ionic compound. Okay, so here is the example. You have to keep in mind that soluble ionic compound, okay, is 100% soluble and dissociate in water. So that's why NaCl, which is a soluble salt, have no Ksp value. Right, so for example, okay, write the solubility product Ksp expression for each of the following. Okay, silver carbonate. Alright, so first of all, you have to write the dissociation of salt. Okay, because salt here is slightly soluble salt or partially soluble salt. So you have to use the reversible arrow and make sure the equation here is balanced. Okay. And then remember salt is exists in solid, whereas for the ion form is in aqueous. Right, so how to write the Ksp? So because the reactant here is in solid, so it is not included in the Ksp. So you can write Ksp equal to concentration of Ag plus power of 2. Because coefficient here is 2 times concentration of CO3 2 minus. Okay. Alright, next, barium fluoride. So first of all, you have to write the dissociation of salt equation. So barium fluoride exists in solid. Alright, and because this is slightly soluble salt, so we have to use reversible arrow. Okay, and it will produce barium 2 plus and 2 mole of F minus ion. Make sure you balance the equation. Next, we can write the Ksp. Ksp is equals to concentration of barium 2 plus times concentration of F minus power of 2. So, for the salt, it's not included because it exists in solid. Okay, next, copper 2 sulfide. So, copper 2 sulfide, copper 2 plus and sulfide S2 minus. When you combine, then you will get CuS that exists in solid. Okay, when dissociate, partially dissociate, it will become copper 2 plus and S2 minus ion. And then we can write the Ksp equal to concentration copper 2 plus times S2 minus ion. Iron 3 hydroxide, iron Fe3 plus combined with hydroxide ion. So when combined, we will get here Fe bracket OH3. The acid in solid. So partially dissociate and become Fe3 plus and 3 mole of hydroxide ion. Now, make sure your equation is balanced. Then we can write the KSP expression equals to concentration Fe3 plus times concentration OH minus power of 3 because the coefficient here is 3. Okay, next for E, barium phosphate, barium Ba2 plus, phosphate PO4 3 minus. Okay, and then we get Ba3 PO4 bracket 2. Okay, which exists in solid. This will partially dissociate, then become barium 2 plus, 3 mole barium 2 plus, and 2 mole of phosphate ion. Write the KSP expression. Make sure equation is balanced. And the coefficient become power of. Okay. Right, next. Tin 2 sulfide. Tin here formula is Sn2 plus, sulfide S2 minus. When combined together, it will form SNS. Okay. So, exists in solid. Okay, partially dissociate become Sn2 plus and S2 minus ion. So, then we can write the KSP expression. Concentration Sn2 plus times Sn2 minus ion. Okay. Alright, next, calculating involving KSP. Alright, so there are two types that involve in the calculation of KSP. The first type is referred to determine KSP from solubility or molar solubility, which means solubility, either solubility or molar solubility is given in the question and we have to calculate the value of KSP. Okay, for type 2 is referred to determine solubility or molar solubility from KSP, which means KSP is already given in the question. We want to calculate solubility or molar solubility. And for these two type of calculation, so you have to use ice table. Okay. So, example number 2. Okay, calculate the molar solubility of PbCl2 and given to you the value KSP here. Alright, sure. What should we do first? So, first of all, you have to write the salt dissociation equation. Alright, since Pb lead to chloride solid is partially dissociate, so you have to use reversible arrow. It will form Pb2 plus and Cl minus. So, balance the equation. So, chloride ion should be 2 mole of chloride ion. Okay, next we draw the ice table. I stands for initial concentration, C stands for change in concentration, and E stands for the equilibrium. Okay, as for the rectangle, which refer to the salt here, is in solid. So, therefore, just write dash. Okay, for the ion, because initially it is not formed yet, so we just label it 0. Not formed yet. Okay. Right. So, same things for the change for the salt. Because solid, so just write dash. Okay. As for the ions, it will increase and refer to the coefficient. So, increase positive S. So, S is referred to the change in concentration. Okay, for the chloride, because we have coefficient 2 here, it will increase positive 2S. Okay, at equilibrium for PbCl2 is solid. That's why we write here dash. Okay, Pb2 plus S, Cl minus 2S. 0 plus S become S. 0 plus 2S equals to 2S. Okay, write the KSP expression. And don't forget because chloride here, we have coefficient here 2. So, power of 2 here. And then substitute the value of KSP. Okay, and also value in the ice table. Okay, don't forget here is power of 2. Okay, we get like this. For S cube equals to KSP. And then you will get this answer. So, S here is referred to the molar solubility. Okay, so the molar solubility of PbCl2, which refer to S, is 1.6 times 10 power of negative 2 molar. or you can write mole per liter. Okay, next example. So, given to you the KSP for copper 2 hydroxide, 2.2 times 10 power negative 20. Calculate the solubility of copper hydroxide in gram per liter, which means we want solubility. Okay, right. So, first of all, you have to write the salt dissociation equation. Okay, copper 2 hydroxide exists in solid, partially dissociate and become copper 2 plus and 2 mole of hydroxide ion. Remember, equation must be balanced. Alright, next, draw the ice table. Okay, as for the solid here, okay, is not included in the ice table. So, because of that, just write dash. For the ion here, initially it is not formed. So, the initial concentration is 0. Change, dash. Okay, and then look at the coefficient for copper 2 plus is 1. So, it will increase positive S. Okay, hydroxide ion, coefficient here is 2. So, increase plus 2S. Okay. So, at equilibrium, for the salt is solid, dash. Okay, for copper 2 plus, 0 plus S is equals to S. For hydroxide, 0 plus 2S equals to 2S. Okay, next, write the KSP expression. Don't forget, hydroxide ion, its coefficient here is 2, then power of 2. Substitute the concentration at equilibrium. Okay, remember power of 2. Okay, and then substitute KSP. So, we will get the molar solubility here is equals to 1.8 times 10 power negative 7. Unit here is molar. Okay, so the molar solubility of copper 2 hydroxide is 1.8 times 10 power of negative 7 molar. However, the question asks here to calculate the solubility. So, because of that, we have to convert from mole per liter to gram per liter. Okay, so because of that, you have to calculate the molar mass of copper 2 hydroxide. Okay, that is 97.6 gram per mole. So, remember how to convert molar solubility to solubility. So, molar mass times the concentration or the molar solubility. So, we'll get here gram per liter, which refer to the solubility. Okay, alright. So, we can cancel out the unit of mole of copper hydroxide. Okay, and finally, the final unit here is gram per liter. Okay, so solubility of copper 2 hydroxide is 1.8 times 10 power of negative 5 gram per liter. Okay, now using KSP to compare solubilities, when we refer to the value of KSP value increase, so therefore solubility also increase. Alright, so you must compare KSP of compound whose formula have same total number of ions. Okay, for example, like between these two equilibrium, okay, magnesium carbonate dissociate become magnesium ion and carbonate ion. So, the KSP value is 3.5 times 10 power of negative 8. Right, so the ratio here is 1 to 1. 1 to 1. Okay, and then for the second example here is lead to sulfate. Okay, dissociate and become lead to ion and sulfate ion. Also, ratio 1, 1, 1. So, the KSP value here is 1.6 times 10 power of negative 8. So, therefore, we can compare both KSP value here. And from here, we notice that the value of KSP for magnesium carbonate, that is 3.5 times 10 power negative 8, is higher compared to the KSP for the lead to sulfate. So, therefore, we can conclude that here, magnesium carbonate is more solubility than lead to sulfate. Or in the other word, magnesium carbonate has high solubility than lead to sulfate. Alright, so now comparison between QSP versus KSP. So what is QSP? QSP is referred to the ion product. So the formula is the same as KSP. Okay, the function of QSP here is to predict the formation of precipitate. Okay, so if the value of QSP is equal to KSP, so the system is already at equilibrium. So solution is saturated and no change occur. So which means that the system does not change direction. Okay, so equilibrium exists between undissolved solid salt and its dissolved ions. This is what we call saturated solution. Okay, we have undissolved solid salt in equilibrium with its dissolved ions. Okay, so if QSP is bigger than KSP, so the solution is super saturated. So which means the system shift to the left, okay, to reach equilibrium. So precipitate forms until the solution is saturated. Okay, until the value of QSP is equal to KSP. Okay, alright, so if the QSP is smaller than KSP, which means the solution is unsaturated. So, which means no precipitate will form. So, the system will shift to the right. So, which means to the undissolved solid salt to reach equilibrium. So, more salt should be dissolved to increase the ions concentration until QSP is equal to KSP. Okay, more solid dissolved. Alright, so next example. So, will a precipitate of calcium sulfate form in solution of calcium 2 plus concentration is 0.025 molar and sulfate ion concentration is 0.03 molar. Giving to you the KSP value here. Okay, what should we do? So, first of all, write the salt dissociation equation. So, calcium sulfate solid partially dissociate. So, use reversible arrow and it form calcium 2 plus and sulfate ion. Alright, so make sure your equation is balanced. Then write the KSP expression. The KSP value is already given in the question here. In the question also already given the initial concentration of calcium ion. Okay, that is 0.025 and also the initial concentration for sulfate ion that is equal to 0.03 molar. Right, so what should we do? Write the QSP expression. So it's just the same like the KSP. Okay. However, the value here, the value of the ion here is referred to the initial concentration. So just substitute the initial concentration for both ion and the value of QSP is 7.5 times 10 power of negative 5. Okay, next step, compare QSP value with KSP value. And we will notice that the value of QSP is bigger than KSP. So, calcium sulfate will precipitate until QSP is equals to KSP. So, meaning that the solution is super saturated and then the system shift to the left side. So, which means calcium sulfate to reach equilibrium. Common ion effect. Alright, so what is common ion? Common, an ion that is common to two or more components in mixture of a solution of ion. So which means the same ion that present in the mixture of solution. What is the effect when there is same ion present in the mixture? So it will reduce the reduction in the solubility of salt in the presence of common ion. So when there is a same ion in the mixture, common ion in the mixture present, so it will reduce the solubility of the mixture. So which means less solid can dissolve. Alright, so what are the effect of common ion on solubility? So the presence of common ion decrease the solubility of slightly soluble ionic compound. So for example, addition of sodium chromate, which is a soluble salt, to saturated solution of lead to chromate. When sodium chromate, that is a soluble salt, is added to saturated solution of lead to chromate. Alright, so the concentration of chromate ion will increase. Okay, so chromate ion here is referred to the common ion. So the same ion that exists in the mixture. Okay, according to the Le Chatelier principle, okay, the increase in chloride ion will cause the position of the equilibrium to shift to the left. Okay, so therefore, sum of chromate ion, okay, will combine with lead 2 ion to form solid lead 2 chromate salt. So thereby, it will cause some of the lead 2 chromate salt to precipitate. So stability of lead 2 chromate will decrease. Alright, so if we look at example, so what is the molar stability of AgBr in pure water and in 0.010 molar NaBr, and giving to you the KSP value. Alright, so what should we do? First of all, write the dissociation equation for the salt. Okay, AgBr is solid, partially dissociate. It will form Ag plus aqueous and Br minus aqueous. Second step, draw the ice table. Since the salt here is in solid, so just write dash. As for the ion, not formed yet, so label 0, 0. Okay, changes refer to the coefficient. Solid is not considered, so write dash. Okay, Ag plus, coefficient here is 1, so increase positive X. As well as the bromide ion also increase positive X. Okay, at equilibrium, concentration of Ag plus is X. Concentration of Br minus ion also X. Okay, write the KSP expression, alright, and substitute the value of concentration at equilibrium and also the KSP. So from here, we'll get the value of X here is 8.8 times 10 power negative 7 molar. Right, so the X value here is referred to the molar stability of silver bromide in pure water. So the unit here should be in molar, or you can write mole per liter. Okay, for B, so first of all, so you have to write the assumption. Let S is referred to the molar stability of AgBr in NaBr. Okay. So which means that we add NaBr into the AgBr solution. The same salt dissociation equation, write the ice table. Solid not considered, write dash. So Ag plus not formed yet. However, bromide ion is already exist. That is referred to the concentration of NaBr. Okay, so 0.001. Okay, as for the chain, so AgBr solid dash, Ag plus positive X, okay, Br minus also positive X, since the coefficient for both ion here is 1. Okay, at equilibrium, so AgBr solid dash, okay, Ag plus is S, okay, Br minus is 0.001 plus X. Okay, we can write the assumption here. So assume S is very small, since the KSP value is very small. So we can assume that 0.01 plus X is approximately to 0.001. So write the KSP expression and substitute all the values. Okay. Right. So from here, we can find out the value of S is 7.7 times 10 power negative 10 molar. So S value here is referred to the molar stability of AgBr in NaBr. Okay, that is 7.7 times 10 power negative 10 molar, which is smaller compared to the molar stability of AgBr in water. Because of the presence of the common ion, that is bromide ion. Okay, so that's all for today. So hopefully you can understand what I taught today. If there is any problem, don't hesitate to ask me. Okay, that's all. Thank you and Assalamualaikum.